It's unfortunate. Okay, so I was talking about Grothendieck dream. So we can think of B as being a Homotopian 1 type, since we just used the information about Homotopian 1 type. So we can think that B is a Homotopian 1 type, meaning that there is no higher homotopical information. E is just from the long exact sequence of homotopy groups. E is then also a homotopy 1 type. So we get a certain covering of groupoids. Covering of groupoids is just a discrete vibration. Discrete vibration. That is a functor. So now I'm writing this for groupoids, such that for any morphism from X to Y in B, and X bar in E over X, there is a unique lifting of a morphism F to a morphism from X bar to Y bar. So now we get the main principle of Galois theory formulated in the following way. Statement. Discrete vibrations bijectively correspond to functors from P1 of B to sets. How do we generalize it to n types, which is precisely the Grothendieck dream, to generalize this correspondence to n types? Well, I can sketch a formulation of such statement. So vibration from E to B, where E and B are homotopy and types, meaning that there are no higher homotopy groups in dimension greater than n, are classified by weak functors. Weak functors meaning that functoriality is just up to equivalence, not a strict functoriality. From B to n groupoids. So sets are 0 groupoids, and this is an extension of what we were trying to do for covering spaces. Well, so Grothendieck showed this for n equal 1, Hermida for n equal 2, and the general case is still open. So we consider a case n equals 1. Let E and B be just groups. And let us fix a fiber F also a group. And then we get a functor which has its image in the following two group. So we get functors which classify extensions, and those functors are functors from B to this capital out of F. And this is a two group of automorphisms of F. What a two group is? Well, it's just a two groupoid with one object. So we have just one object, morphisms, which all are invertible, and morphisms between morphisms, which are also all invertible. So algebraically, we're saying that all extensions of the following form are classified by functors from B to automorphisms of F. So they classify these extensions. So let us describe this category out of F more explicitly. First, F is a unique object. This is quite unsurprising, since this out of F is supposed to act on this on F, and F is precisely the thing that this whole category acts on. So an automorphism of F is an arrow from F to F. And what are two morphisms? So we have elements of the fiber F such that so let alpha and beta be automorphisms of F. I write it for just the ordinary group of automorphisms. And we describe two morphisms. So a morphism between morphisms is precisely such G's which conjugate one automorphism into another one. So we get two regular automorphisms from, well, maps from F to F. And then between them, we get a two morphism G, which conjugates one automorphism into another one. So out of F is a subcategory in groupoids with unique object F. So now we want to say a bit more about classifying short exact sequences of groups. So once again, consider a short exact sequence. Classifying short exact sequences of groups via set theoretic sections. Yeah. So consider a section here. Let me denote it some way. Yeah. So for any B in B capital, we have an automorphism. There is an automorphism of F given by alpha of B acting on F is equal to S of B acting on F, S of B to the power -1. So obviously S is not a homomorphism of groups unless an extension is split. So we don't in general have, well, basically the construction I'm describing now will be very similar to the gluing co-cycle in fiber bundles, if someone is familiar with this construction. So we have a failure of associativity here. Of S being a homomorphism. So we don't have this equality. However, we have an equivalence. This equivalence is given by the following. So the product of alpha B prime conjugated by certain element of F is equal to this product. So G can be expressed like this. It's the product of this form. Yeah. Yes. To the power -1. So we get a weak two-functor. So here we already see that the functor should be weak because we don't have functoriality, but we have a weak functoriality. That means that we have functoriality up to equivalence. So we get a weak functor B alpha from B to this category out capital of F. So equivalent to functors give equivalent extensions. And this set of maps from B to out of F is called non-abelian cohomology of B with coefficients out of. So this is very similar to all this Czech business when we create this gluing cocycle. Okay, so what we established here is that extensions between F and B are classified up to two categorical equivalence by weak functors between B and out F. So this is a two category. This is also a two category. And those two categories are equivalent. So this was a snapshot of Grothendieck dream. but we will meet it later when we will talk about relationship between categorical decomposition of morphisms and Postnikov towers. So basically, Grothendieck dream is a way of going between category theory and topology, but more on that later. So now we will just say something about n categories in general. Bayes calls it the power of negative thinking. The reason is that we will not only see what n categories is for non-negative n's, but also what n categories are for negative n's. Okay, so first of all, we can try to understand what are n plus k categories. Okay, so for sorry, n categories. So for 0 and 0, yeah. So what do I mean by, well, that's not, okay, I will denote it like this, but I'll explain what I mean. So if j is lower than k, then, so n is the usual n in n categories, meaning that we have morphisms from 1 to n, from 0 to n, if we count objects as morphisms. And k means that we don't have any morphisms in dimension lower than k, except for identical ones. No non-trivial morphisms. So the good topological way to think about what is happening is that n and k give us certain range where we can have homotopy groups, and we don't have homotopy groups below k and above n. So that's the basic idea. Okay. So for 0 and 0, we have sets, just discrete objects. For 1, we have categories. For 2, we have 2 categories, and so on. Here we have commutative monoids. Here we have something called braided monoidal categories. Here we have monoidal 2 categories, and so on. So yeah, here we have everything below here is the same as this guy here. So here we have symmetric monoidal categories. So here we have braided monoidal 2 categories. I mean, for now, those are just empty words, and I think they will remain empty. I'm just showing some kind of a table. The main idea here is that after some iterations, the table should stabilize. And the curious thing here is that we actually don't go all the way up here. So here it stabilizes here, and so on. And so we have a diagonal that should end somewhere here. Somewhere here, maybe, yes. And so this is the reason that suggests that we should also have -1 categories and -2 categories. So in order to understand what these are, we will have to, first of all, I can give an answer already. So -1 categories consist just of 2 objects, true and false, no morphisms. And -2 categories, it's just, there is just one -2 category, which consists of only one object, necessarily true. So how we will understand this? Well, we need to understand, first we need to understand something about general n categories. So something about general categories. So first of all, any n category is in fact n plus well, n plus 1 category and so on. We just don't have any higher morphisms. So for n morphisms, we have no equivalences, just identities. So that's the basic idea behind all these higher categories. We should keep track of equalities. So we replace equalities with equivalences, and we keep track of the morphisms which realize these equivalences. And that's the basic idea. And if we don't have any higher morphisms, then we don't have equivalences. We have just strict, well, we have equivalences up to identical morphism, which just means strict equality. Okay. So in the same way, any n category is an infinity category. So infinity category is just like a direct limit of n categories. We just have morphisms for arbitrary large n. And so the set of, so all morphisms in dimension higher than n for an n category are just identities. Okay. And also inside, so that was the first point about n categories, is that in dimension n we don't have equivalences, we just have we don't have equivalences, we just have equalities. The second point is that we actually can find small in very mundane sense of the word, small n subcategories in the following way. So inside any n category, there are small n subcategories. for example, let C be a 3 category. And then, we have two objects, two morphisms between them, two morphisms between those one morphisms, and one morphism between those two morphisms. So this is a very little three category in this case, which can be denoted by home category between two objects. So this is, since we consider these now as objects, this is now 3 minus 1, aka 2 category. So we have one morphisms being two morphisms, and two morphism being a three morphism between two morphisms. So in general, yeah, so here I should write n minus 1. In general, Cxy is n minus 1 category for n category C. We can continue this construction, and if we have two parallel J morphisms, for example, those can be parallel two morphisms, then home between them is n minus J minus 1 category. So we can use this equation to obtain -1 and -2 categories. How we're going to do that? So a trick. Consider home category between two objects where X and Y are two n morphisms. Then what we get here? Well, we get n minus 1, okay, -1 category. So as we can recall earlier, I said that n morphisms don't have equivalences, they just have equalities. So that implies that if we have two morphisms which are in two n morphisms, then home between them consists just of 2 points. So true and false. Why can we call them true and false? Well, obviously because one of them means that those two morphisms in fact coincide, and the other means that there are no morphisms between them, and that means that they're different. Because once again, we don't have equivalences, we don't have equivalent morphisms of top degree, we just have equal morphisms of top degree. So actually we have established that -1 category consists just of 2 points. And we can actually prove that there are no other -1 categories, but I will not do this right now. Well, it's just a simple exercise, so maybe I can leave it for exercise proof. There are no other -1 categories. So similarly, if we have J equal n+1, that is, we have two parallel n+1 morphisms, and we remember that there are no n+1 morphisms except identities. So parallel n+1 morphisms means that it is an identity on the same object. Thus, they're equal. And we have the only object equal to necessary true, because we don't because all parallel n+1 morphisms coincide. So we have a unique two category. Okay. So actually, the idea of proof that there are no more -1 categories is that one may try to embed this category into an arbitrary n category and see that the only possible way for it to exist is when it has only two objects and no morphisms. Okay. So now we're ready to talk about homotopian types. And I will formulate precisely now what is a Grothendieck dream. A Grothendieck dream. So homotopian types. Okay. Structure. The hypothesis. Grothendieck dream is the following: that n groupoids is equal to n homotopy types. So, like we've seen before, it is natural to expect that we can classify all n homotopy types by considering weak functors. Well, all covers of all fibrations with n homotopy types as weak functors to n+1 groupoids. And so a similar statement here is that actually n groupoids and n homotopy types are the same thing. So if we think of it, yeah, okay. So I think that, well, basically another way to say it is that we can build a topological space or a simplicial set from stages of groupoids. And if we end at the stage number n, then homotopy groups should also end at the stage number n. This is in contrast with the usual, for example, construction of cellular subdivision, where we obviously don't, where we obviously can have higher homotopy groups, but here, since we construct everything from groupoids, we don't have such problem, and that's the basic idea behind Grothendieck dream. But now I will clarify a bit what does it mean, what the statement means. So I said some intuitive words, but now I will formulate it more clearly. So n groupoids those are just objects where those are just categories where everything, meaning every morphism, everything is invertible up to high equivalence, up to higher morphisms. So obviously it's an n category. And so in particular, n morphisms are just strictly invertible. So this thing here should be properly called weak and groupoids. The word weak means that up to equivalence. We consider everything up to equivalence, weak and groupoids. And they should be equivalent, Quillen equivalent to spaces such that in J, for J greater than n, should be equal to 0. Okay. So that's the basic idea behind Grothendieck dream. One can see that on one side we have something categorical and groupoids, and on the other side we have n homotopian types. And so if we believe in this hypothesis, then a certain statement about category theory can be formulated purely topologically and vice versa. So from purely categorical statement, we can get a homotopical one. For example, later, as I already told, we will derive the fact that each space has a Postnikov tower using this hypothesis from the fact that each functor has a factorization as a certain sequence of functors between, well, a certain sequence of functors with certain properties. So they should be surjective on certain classes of morphisms. Each functor decomposes in this way, and this will later yield the Postnikov tower. So I'm just explaining how Grothendieck dream relates topology and category theory here. Okay, so since we introduced negative n categories, I can also introduce negative homotopic groups. So definition. Negatively graded homotopic groups. So Pj is equal to x. Pj of x is equal to 0 if for any spheroid we have J. There is a disk of dimension J plus 1, which when restricted to the boundary of the disk equals F. So X is a 0 homotopian type if all higher spheres are contractible. What does it mean in practice? Well, in practice, it means that X is a union of connected components, each of which is equivalent to a point. A disclaimer, I will only consider compactly generated Hausdorff spaces for which there are no, well, I'm not sure that this is enough. Okay, I will consider space is not nice enough that I don't have to care about the fact that it is weakly equivalent to a point. It's just equivalent to a point. Okay, so in a similar way, we can describe a homotopy -1 type. So this is a homotopy 0 type, such that for any s0 to x, there is d1 to x, such that they coincide. So now it just means that x should be at least up to homotopy either empty or a one-point set. Now, what is a -1 sphere? Well, a -1 sphere is just a sphere inside the space R0, which is empty. And D-1 is a disk inside of the space R0. Well, this is just standard. We standardly define a sphere as set of points, as a set of unit of vectors of length 1 inside of a space Rn+1. So here I just wrote it for R0. So D-1 is just this. And so -2 type is precisely is always one-point set. Up to obviously up to homotype. Okay. Now since I already described what is a homotopy -1 type and homotopy -2 type, I can now talk about this categorical part of the story, which I promised. So this section is called stuff, structure, and properties. And I will tell something about forgetful functions. What is a forgetful function? Okay, so first of all, in order to explain what I mean by stuff, structure, and properties, I will consider a concrete example. G is a set, which is some kind of stuff, plus structure, multiplication. Multiplication gives us structure. Plus properties, which are just group equations. So we know that the operation should be associative, have left and right units, which coincide. Each element should have an inverse, and so on. And now we can consider an example, several examples, in fact, of forgetful functors. Okay, so P is a functor, and P forgets nothing. That's just an identity functor from abelian groups to abelian groups. Second, he forgets properties. We can forget the fact that an abelian group is abelian and just consider it as an arbitrary group. We forgot property, which is just an equation, AB is equal to BA. So we forgot properties. That is another kind of forgetful functor. He forgets at most structure. So that's a functor from abelian groups to sets. Yes, which is just forgets the structure of a group on a set. And finally, P forgets stuff is when P is in fact an arbitrary functor. So in the notes, we have the following example. It's a functor from pairs of sets, which just forgets the second coordinate. Okay. So actually, as we will see in just a few moments, this condition that functor forgets something is in fact homotopical. So the more the functor forgets, the richer the fiber is in the sense of homotopy theory. So each functor obviously has a fiber. And if it, for example, forgets nothing, then the fiber over a point is just a fiber over an object is just an object. So it's homotopically trivial. If it forgets some properties, then the fiber can be richer. For example, the fiber can be richer. I will explain it in more detail in a few moments. So I will now say something about homotopical preimage. So I should specify that the word forgetful functor here is purely decorative, because actually any functor is forgetful in some sense. So as I said, a functor that forgets stuff is an arbitrary functor. So you can't really pin down what a forgetful functor is. And that's basically, I think, well, I think it should be well known, since it is really hard to find a definition of forgetful functor. So sometimes functor to sets, it's called forgetful, but this is somewhat arbitrary. Okay. So we have a forgetful functor. Consider an object X and B. We can consider its preimage. Or rather, an essential preimage. Which means that we close this preimage under all equivalences. So it consists of objects E and in E capital, such that projection is equivalent to X. and morphisms there are just morphisms which are preserved by projection. So those are morphisms in E, such that they are mapped to morphisms in B and the following diagram computes. Okay, so let's consider an example. If E and B are groupoids, then P forgets structure if the fiber is one groupoid. For example, we can consider forgetful functor, which was described above. So we just map it like this. And so we have a whole groupoid of possible, it has a full groupoid of possible y's here, which are in the fiber over X. So that's an example. So obviously, those suggest zero groupoid. Okay, so I'm sorry, I just was clearly a mistake. So it forgets stuff because I was wondering why it didn't add up. So it forgets stuff if the fiber is one groupoid. So and this was an example when we forget stuff. So that's precisely how it's supposed to work. So F forgets structure now. The fiber is zero groupoid. Just a set. So we had a functor from a billion groups to sets, and we have a set of ways to endow a set with the structure of an abelian group. Finally, P forgets properties if the fiber is -1 groupoid. This corresponds precisely, so 1 or 0. So this corresponds precisely to the situation where we projected from abelian groups to just arbitrary groups. And so if you have a group, you have like two possible answers. Either it is abelian or it is not abelian. So this precisely corresponds to those two values. Okay, and if it gets nothing, then the fiber is just -2 groupoid, which is just a point. Because, well, you basically don't have any information lost if you have a functor that forgets nothing. So yeah, this is pretty natural. Okay, so now I think I can start explaining the relationship with topology. I don't know. Are there any questions so far? Okay. If not, then I will just continue. So first thing I want to talk about are factorizations. And those are precisely those Poisson towers in category theory that I was talking about. So consider an infinity functor, meaning that it just preserves up to equivalence composition of n morphisms for arbitrary large n, infinity functor. This is called n surjective. If we're given parallel n-1 morphisms, E and E prime, E, and for any n morphism F n times to E prime, there is, so this is happening in B. There is F tilde, which covers it. So the definition is pretty natural. We just require that on n morphisms, the functor is surjective. Essentially surjective. So we consider everything up to equivalence. Consider an example. Consider a fibration of sets. So P is 0 surjective. So is 0 surjective if P is surjective. Since all 0 morphisms are just identities. So it should be surjective on identities, meaning it is surjective. Or better say essentially surjective, because we have everything up to equivalence. equivalence. And a surprising thing is that P is once surjective when it is injective. So why is that? Well, if we have a morphism in sets, meaning that we just have an equality here, since those are just discrete sets, meaning that by our assumption, there exists an equality between pre-images. So if we leave the one morphism, which is just identity, we should get another one morphism in sets, which is also just identity. So that means injectivity, precisely injectivity. And now note the following. So surjective and injective maps form factorization, system on sets. So each morphism can be uniquely decomposed into the composition of zero surjective, meaning just surjective morphism to E prime, and an injective or one surjective morphisms from E prime to B. This is quite clear. E prime is just an image. So if this is P, this is just an image of P, and this is an inclusion of this image into P. Now we can make a step up and consider a functor between categories. So here, zero surjectivity once again corresponds to essential surjectivity. Essential surjectivity. One surjectivity corresponds to the fact that the functor is full, meaning that it is surjective on a set of morphisms in the image. It is too surjective if it is fully faithful. And it is three surjective. It is arbitrary. So three surjectivity condition does not yield anything. So the first assertion is pretty obvious. We just seen it for sets. Now about one surjectivity. As I already said, this one follows from the fact that it should be surjective on arrows, meaning that it's just surjective on precisely those arrows which are in the image of the functor restricted to objects. And now the most interesting part is about two surjectivity. Two surjective is the same as surjective on equalities between morphisms. This is precisely a condition of the functor being fully faithful. So note that if we add up conditions 0, 1 and 2, P is an equivalence because it's surjective on objects and fully faithful. Yeah, I don't think that it's just faithful here because we don't know anything about surjectivity. Yeah, we don't know anything about surjectivity on one morphisms. No, wait a second, that can be right. No, everything was okay. So it's fully faithful because any one morphism can be represented as a trivial. No. So okay, so it's just faithful because well, the argument is similar to showing that one surjective functor between sets is in fact injective, and here we have the same thing, but for categories. So it all relies on this philosophy that in the top degree we don't have equivalences between morphisms, we just have equalities. So here it is very similar. The functor is faithful because if we have surjectivity on equivalences, that means that any two morphisms which coincide in the image should coincide in the pre-image. Okay, so now we can formulate these four conditions which said something about forgetting structure or stuff. Okay, so first, forgetting nothing. Is just 0 plus 1 plus 2. Forgetting most properties is just 1 plus 2. Forgetting at most structure is just 2. And so finally, forgetting stuff is just 3 because forgetting stuff is an arbitrary factor. And now we also have a factorization. So we can turn any category along the functor P into its image category using the following procedure. So here we first of all have 0 plus 1, meaning that it is surjective on objects, and it is full. Here we have 0 plus 2, also surjective on objects, and faithful. Finally, here we have 1 plus 2, meaning that it is not necessarily surjective on objects, but on this part of the image on which it is surjective, it is fully faithful. So the procedure is very similar to that in sets. So how do we construct such factorization? We start from E, so procedure to construct such factorization. From E, then we add two morphisms. Equalities between one morphisms in B. So we map some morphisms, they become equal in the image. We add those two morphisms into category E. And we get category E prime. It is evident from the definition that the functor is indeed 0 and 1 surjective. Then to get E2 primes, we just add one morphism. So here the functor is also surjective on objects because we didn't change the class of object, but it may be not surjective on morphisms. However, if we had two equal morphisms, then their preimages are also equal. That's condition number 2. And finally, to get B, we add missing objects and arrows not okay. So we now have this kind of factorization, and we can write the following. The result, get the following. Functor forgets just stuff. It is 0 plus 1. Functor forgets just structure if it is 0 plus 2. Finally, functor forgets just properties if it is 1 plus 2. Okay, so I think I will just consider an example and we will finish here. So an example of such factorization is the following. So we can take category of pairs of vector spaces, which is mapped to just the forgetful functor to sets from the first one. Then we have a factorization like this. So objects of E prime are just pairs BW such that BW are vector spaces, and morphisms in E prime between such pairs are just linear morphisms between the first components. Now, so that was E prime. E2 primes is the following thing. So objects E2 prime are forgetful functors V such that so we just considered a functor which is surjective on objects, but we removed the second coordinate. And morphisms in E2 primes between two such objects are just all set theoretic maps between them. So this is a gradual transformation from category of pairs of vector spaces into a category of sets. Okay. I think that we're pretty close to Plesnikov towers. However, I did not manage to reach them today, but hopefully I will be able to do it next time. So I think I should stop here.